We will now begin solving problems into our current topic, that is ultimate strength design. For problem 1, a precast concrete slab is 1.2 meter wide and 150 mm thick. FC prime is 21 megapascal and Fy is equal to 275 megapascal. Consider the center of reinforcement. AS is 30 mm from the top of the slab. The problem gives us these three situations. The first one is calculate the value of AS in millimeter square corresponding to 60% of the reinforcement that will produce a yield strain in the steel at the time the compressive concrete strain of 0.003 is reached. Number 2, if AS consists of 620 mm diameter, determine the nominal flexural strength of the section in kilonewton meter. And number 3, if the section has a cantilever span of 2.5 meters, calculate the total factored uniform on the slab in kilopascal. We can notice in this problem that on the third situation, if the section has a cantilever span, so this slab is a cantilever 1. That's the reason why AS is located 30 mm from the top of the slab. Since for cantilever slabs or cantilever beams, tension will be the top portion of the beam and not the bottom portion. We will now start in solving the problem. Situation number 1. It gives us the condition produce a yield strain in the steel at the time the compressive concrete of 0.003 is reached. From the derivation of formula, the term the concrete will theoretically fail at strain of 0.003 and the steel will fail simultaneously yield correspond to the balance condition. So the reinforcement ratio that was derived from that condition is called raw balance, and it's equal to this equation. So for problem number 1, it is asking the value of AS at 60% of raw balance. But before we can compute for raw balance, we need the value of beta 1. For FC prime less than 28 megapascal, beta 1 is equal to 0.85, and since our FC prime is 21 megapascal, we will make use of beta 1 equal to 0.85. If we will now substitute the value of FC prime equal to 21 megapascal, beta 1 is equal to 0.85 and Fy is equal to 275 megapascal, we multiply it by the quantity 600 divided by 600 plus Fy which is equal to 275 megapascal. We can obtain for the value of raw balance equal to 0.03783, and the 60% of that value, that is 0.6 multiplied by raw balance, is equal to 0.0227. If we try to solve for the value of D, it is given on the problem, the thickness of the slab equal to 150 and the location of reinforcement from the top portion of the beam, that is 30 mm. So if we subtract 150 to 30, we can find for the effective depth equal to 120 mm. So we can now solve for AS, that is equal to 0.6 raw balance or 0.0227 multiplied by the beam width, that is 1200 on our problem, and 120 is the value of effective depth. We can have this value for AS, and that is our answer on the first condition. For the second condition, if AS consists of 620 mm diameter, determine the nominal flexure strength of the section in kilonewton meter. From the derivation of formulas, we can remember that Mn is just equal to tension multiplied by the moment arm D minus A over 2, or that is just equal to AS Fy multiplied by the effective depth minus the depth of the compression block A divided by 2. So using this formula, we can solve for problem in condition number 2. We just first obtain AS, and that is just equal to 6 pieces 20 mm diameter reinforcement. So we can calculate the area from the simple formula pi d squared over 4 multiplied by the number of pieces, that is 6. So we can have the value that is equal to 1884.96 millimeters squared. For depth that is computed before, and it is equal to 120 mm, and for the depth of compression block that can be computed from this formula ASFY divided by 0.85 FC prime B, so that is derived from C is equal to T. If we will now substitute the value of AS equal to this value, then we multiply it by Fy, that is 275 megapascal, then we divide by 0.8521, that is FC prime, and B is 1200, we can have the value of the compression block, that is 24.2 mm. And if we substitute the value of ASFY, D minus A over 2 into our equation, we can have now the equivalent nominal moment. We divide this with 10 raised to 6 to convert Newton into kilonewton and mm into meter, and that is equal to 55.93. In the third condition, if the section has a cantilever span of 2.5 meters, calculate the total factor uniform the slab in kilopascal. Here is now our beam. It has a load of intensity W in kilonewton per meter and the length is 2.5 meters. It is supported by a fixed support at the left part of the beam. We can calculate the fixed moment reaction MU by solving first for the resultant, that is just equal to the area of the uniformly distributed load and the moment arm, which is equal to the distance divided by 2 of the length of the beam, since resultant is acting at the centroid of the uniformly distributed load. So R, that is equal to the area of uniform load, and it is just equal to the length multiplied by the intensity of load, and X can be calculated equal to half of the length of the beam, that is 1.25 meter. We can now solve for MU, and that is equal to 2.5 W, that is equal to our resultant multiplied by the moment arm 1.25 meters. This value of ultimate moment was derived from the cantilever beam. If we try to analyze the condition given the problem, condition B and condition C is relative to each other, and C is continuation of condition B. In problem B, we have already calculated value of nominal moment equal to 55.93 kilonewton meter. After multiplying Mn into P, that is the reduction factor for bending, we can have the value of Mu. But since our code limit is strain in tension equal to 0.005, to have a value of P equal to 0.90, we have to calculate first for the value of strain in tension or epsilon T in our problem, for us to determine if the reduction factor in bending is 0.9 or if it is on the transition region, we have to compute for the value of that reduction factor. So from our previous calculation, A is equal to 24.2, we divide that by 0.85, we can have the value of C equal to 28.47 mm. And from this strain diagram, we can have the value of strain in tension. By similar triangle, we can derive it from this equation, and that is just equal to 120 minus C multiplied by 0.003 divided by C. If we will now try to calculate 120 minus C in our problem, that is just equal to this value, 91.53 mm. So strain can now be calculated. 120 minus C, that is equal to 91.53 multiplied by 0.003 divided by the value of C. We have calculated before, that is 28.471. So we can have the strain in tension, that is equal to 0.0096. It means that it is greater than 0.005, that is a ductile section. We can use the value of P equal to 0.9. So we will now multiply Mn into P, and that is equal to 50.34 kilonewton meter for the value of ultimate strength. If we will now equate the value of ultimate moment from the cantilever beam, 2.5 W multiplied by the moment arm, 1.25 meters, into the ultimate moment from the given cross-section and reinforcement, the only unknown will be the uniformly distributed that should be loaded on the cantilever beam that will reach the ultimate moment that the beam can resist equal to 50.34 kilonewton meter. So the uniformly distributed load will be equal to 16.11 kilonewton per meter. But the problem is asking the value of uniformly distributed load in kilopascal and not in kilonewton per meter. We have calculated the uniformly distributed load equal to 16.11 kilonewton per meter. Since our cantilever slab have a length of L, 2.5 meters, and width of 1.2 meters, it means that if we divide 16.11 kilonewton per meter uniformly distributed load into 1.2 meters, it will be loaded uniformly on top on the slab shown on this figure. So we will now divide 16.11 into 1.2 meters, so we can have the uniform load on top of the slab equal to 13.42 kilopascal. I hope that you have learned a lot from this example. Those who want a copy of this file in PDF, just like and subscribe. Comment down your email below and I will send it to you. Thank you.